I think I'm first speaker. I want to at first say thanks to organizers for that opportunity to take part in that conference. And also, I want to mention that this research is the joint research with Grigory Gennadievich Amosov and Aleksandr Nikolaevich Pechin. I will tell about one interesting application of operator theory in quantum information. I will not speak a lot about quantum error correction that is in that title, but I will give the description of the problem and of all objects in that problem. At first, I need to introduce the operator system. So non-commutative operator graphs in terminology of quantum error correction. Let me have Hilbert space, the subspace in space of linear bounded operators called non-commutative operator graph or operator system if it has such two properties. Identity operator lies in where, and if some operator belongs to where, then conjugate also lie in where. Okay, what is the set of quantum errors or quantum noise? Let me have two Hilbert spaces, HA and HB. Here, index A and B is the name of quantum systems. The HA and HB is the Hilbert spaces of pure states. Let me have such Hilbert spaces, and the quantum errors or quantum noise is the set of completely positive trace preserving maps from operators on HA to operators on HB, defined by our set of operators Bj from HA to HB, operators with satisfying that property, and the noise is defined in such way. We take cross operators from the span of Vj. That form of completely positive map is a general form. Each completely positive map have such expansion. So it is very general description of errors. Okay, and what is to define the correction operation or to define the quantum error correcting code? To consider the correction operation, we need the subspace in space HA and one more completely positive trace preserving map called decoding channel from HB to operators on HA, such that following equation holds true. So the states, pure states from code maps to proportional vectors, proportional to the initial state. Okay, and with such noise, definite with BJ connected, unique non-commutative operator graph. Definite by also by BJ here. Indexes not the same, M and J, and that operator graph is very important to the problem of quantum Year correction. But at first, I want to introduce another problem. If the back problem, if we have some operator graph, for example, parameterized by not by such BJ, by some other generating set like here VS, may be definite in some other terms. So how to find the set of errors to that this graph, abstract graph, corresponds in that sense. It is the interesting problem, I think. And it is important because we have such condition. Let we have noise and correspondent graph when the subspace S is a quantum Year correcting code, if and only if the following simple equation holds true here. That means that that space of operators is one-dimensional. The PS is orthogonal projection on code. And it describe codes in terms only in terms of graph. It is interesting. So we can, in some sense, forget about initial problem and pose it only for graphs. And if we have some parameterization of the graph, we can try to describe in that terms the codes, and then solve our back problem, and we will have the full picture. Okay, here it is necessary to mention that we will call the orthogonal projection PS an anti-clique. It is the term from classical graph theory for non-commutative operator graphs was developed the non-commutative graph theory by some errors, and they calculate a lot of characteristics for of classical graphs for such non-commutative graphs, and also an anti-cliques. This is a definition of anti-clique, and here preserved such connection between classical and non-commutative case. In infinite dimensional case, in fact, that condition only is sufficient condition. It is possible to define the codes that doesn't have such condition, but that condition guarantee that the subspace is a code. And also we interested only, of course, only in non-trivial codes, in codes that has dimension at least 2, because we want to code the information by the states we will support in the code. So we need at least 2 distinguishable states in code to code any information, bit or qubit of information. Okay, so it is meaningful to pose the problem of quantum error correction to the graphs separately from initial formalism of noises. Here is some solutions, but let me go further and give the definition of POVM. Let me have some set and sigma algebra of subsets of that set. The set of positive operators on some Hilbert space is a POVM, positive operator valued measure, if it has the following properties: on empty set is 0, on whole set is identity operator, and it is countably additive. The POVM, because of this property on whole set, it identity operator, and because of positivity, linearly generates the operator graph. And in fact, it is possible to show that in separable case, any non-commutative graph is generated by some POVM. So it is nice candidate for type of generating set for non-commutative graph. Is in some sense it's universal type of generating set. So let me consider the POVMs with some additional specific structure, covariant POVMs. Let this set T be the compact group G with normalized Haar measure. And the sigma algebra B is generated by compact subset of our group. Also, let me have unitary, continuous projective unitary representation of our group in the space of operators on some Hilbert space. And when we have, we can define the action by this expression, the action of element on bounded operator. And when POVM, of course, of operators acting on H is said to be covariant with respect to that action, if the following holds for each element in G and each set in sigma algebra. The covariant POVMs have nice structure, nice description, but to say. They have following realization as the integral with density. This density is definite with one positive operator. So the POVM generated by covariant POVM has also nice generating set. because it all works in finite dimensions. So in finite dimensions, it is possible to define in terms of that representation sufficient conditions of correctability for graph generated by covariant POVM. Suppose that we have POVM covariant with respect to representation UG and consider spectral decompositions. If one of orthogonal projections of all of spectral decompositions is constant, then that projection will be the anticlick for the graph generated by POVM covariant with respect to that representation. And in finite dimensions, we can present the series of examples corresponding to various various groups defining the dynamics of quantum systems. By the same scheme, we generate the non-commutative operator graph with the generating set of the same type as here. But here we get the problem on that positive operator. If we consider Q to be positive, when we automatically have closedness under conjugation, but we should show that identity lies in graph and that our graph has the quantum error correcting code. It is possible to show for some quantum systems, but at first I want to speak a little bit about that back problem. It could be solved. One solution could be presented. Of course, here could be much more solutions, but one could be given for the graph generated by POVM by Nymark dilatation construction. Any POVM could be dilated to the larger Hilbert space, and this dilatation E will be the projection valued measure, not only positive valued measure. And let us consider the errors of such form, then that graph corresponds to such errors. Okay, now let me present the examples. First example will be in the dynamics of two-dimensional oscillator. Consider the Schrödinger equation with such Hamiltonian. It is Hamiltonian of two-dimensional oscillator. It is operators of momenta. It is coordinate operators, and introduce such unitary group. The action of group U T could be examined in terms of covariant states. Consider such covariant states with such as vectors in L2 with such formula, and also introduce such products. If we consider such system over complete system of vectors in L2 of R2, it is complex valued functions of real argument. Then we consider we introduce the factorization into the tensor product of such space, and the dynamics ut could be examined in terms of that over complete system. We have such formula. Also consider additional system of covariant states with such wave functions, and define the positive operator by that rule. It's possible to show that this positive operator is orthogonal projection, and it, in that sense, generates the non-commutative operator graph. And for that graph, it is possible to show that it has the anticlick, moreover, maximal anticlick. Of course, if we have some anticlick, then all sub-projections of that anticlick also will be anticlicks for that graph. So it is meaningful to define the maximal anticlick if such projection, if some anticlick cannot be extended, then it is the maximal anticlick, and it is possible to define the maximal anticlick for that graph V. How much time I have? I have 5 minutes, so I want also present the example for Jaynes-Cummins model. Our example is for the two-dimensional system coupled with the field, describing the dynamics described by Jaynes-Cummins Hamiltonian. This such Hamiltonian, it is operators of creation and annihilation, this coupling rate, and it is parameters of field and system, frequencies of field and system. So for such Hamiltonian could be diagonalized in terms of such eigenstates, and also consider the eigenenergies and one specific covariant states called Gazot-Lauder covariant states help to define the operator graphs when we divide by some specific linear from some specific linear structure of the eigenstates of that model. We consider two sequences of eigenenergies and for where we consider the tails which are strictly increasing. And when we divide the whole space on which acts that Hamiltonian into three sequences of into three direct summons, H1, H2, and H3. And if in H1 and H2 consider the so-called Gazok-Lauder covariant states with the by the specific weights and specific formulas, then it is possible to define the non-commutative operator graph generated by the projections on that Gazok-Lauder covariant states and dynamics given by Hamiltonian of Gazok-Lauder of Jaynes-Kamen system. And for such non-commutative operator graph, it is possible to define the anticlick. Okay, thank you for your attention. I think the last part was quite fast, but we have no time.
Thank you, Aleksandr, for the very interesting report. But you have 4 minutes, and since you finished your report, let us discuss your results. Have you any questions about this report?
Maybe you can discuss more the last slide. What is the difference between this result and the result concerning two-mode molecule?
Okay.
Here we have finite dimensional anticlick. That is one of that is projection on the one of three direct summons. It's projection on the direct summon that has not strictly increasing eigenenergies. And here we define in both cases, we define the proof that property, that identity lies in that space in graph through the property of covariant states. And here we defined two sets of covariant states, one in one summoned H1 and one in another. Here we use only one system of covariant states, so maybe it is something mathematically new for that system, I think.
Thank you. Other questions, please? Thank you. Let us thank the speaker again.